Welcome to our talk. Our talk is about the computational complexity of a search problem that is associated with the version of the classical ham sandwich theorem. This is work by Man-Kwun Chiu, Aruni Choudhary, and Wolfgang Mulzer. Let us first recall what the classical ham sandwich theorem tells us. So let's say that in d-dimensional Euclidean space, we are given d finite masses. Then the theorem says that there is a hyperplane that bisects all of these masses simultaneously. As a simple example, we have two masses in the plane and the line shown divides the areas into half. There is also a discrete version of this theorem where the masses are now replaced with finite point sets, and again there is a hyperplane that bisects each of the point sets. As a simple example, here we have point sets from two colors and this line divides both colors. More precisely, both half spaces determined by the hyperplane contain no more than half the point for each color. Ham sandwich theorem has been proven using the Borsuk-Ulam theorem, and then there are no assumptions on the points. The computational problem associated with this would be to find this bisecting hyperplane. Now, since this hyperplane already exists, this is a total search problem. This is also in NP. In fact, it belongs in a complexity class commonly called TFNP. Recently, it was also shown that this is complete for a subclass of TFNP. Let us now ask a more general question. Let's say we have those point sets from before. Let us assign each of them a unique color. And now we also have a vector alpha, where alpha I is at least 1 at most the size of ni. Then a natural question to ask is, can we find a way to divide these point sets such that we get alpha I points of pi? More precisely, can we find a hyperplane H which has some orientation so that the positive half space contains alpha I points of pi for all I? In this simple example over here, we have two point sets in the plane, and the space above this line contains 3 green points and 4 violet points. In this case, we can try many different combinations of alpha I, alpha 1 and alpha 2 for the green and the violet points. If we move these point sets a little bit so that the convex hull of the violet points is inside the convex hull of the green points, then we see that whenever we want precisely 1 green point and 1 violet point, that is not possible, because whenever we take a violet point, we must include a lot more green points. That suggests that the answer to this question is true, but only under certain conditions. And this was shown by Steiger and Zhao in 2010. Preceding this result was a continuous version where instead of discrete point sets, we had convex sets, and alpha I was simply a parameter between 0 and 1. This seems very much like a generalization of the classical ham sandwich theorem, but as you will see later, this is not the case. This is our example from before. We see that this line passes through precisely 1 green point and 1 violet point. Such a set is called a colorful set. That is, it contains precisely 1 point from each color. And a colorful hyperplane is one which is incident to a colorful set. We will only be interested in colorful hyperplanes or colorful sets as solutions, because it is easy to define orientations for such sets. Let us now look at the conditions required for this theorem to hold. As you might expect, you would like the point sets to be kind of well separated. More precisely, if we take a subset of the colors, then the points coming from those colors must be strictly separated from points of the rest of the colors. Now, this is quite expensive to verify whether a point set is really well separated. However, there is a short certificate of violation. It is an index set of two sets of colors such that the corresponding convex hulls are not strictly separated. Equivalently, if we have a colorful set that has affine dimension d-2 or lower, then that also serves as a certificate that well separation does not hold. There is one more condition. So here we have 4 green and 2 violet points, and this line is defined using either of these green points and either of these violet points. So there are 6 colorful sets defining this line, and this gives a solution for the alpha vector 4, 2. However, if we want a solution for alpha 3, 1, so we want exactly one violet point, then no matter how we try, we cannot get a solution. This suggests that we need some kind of weak general position for the point set. Also, weak general position is very difficult to verify, but there is short certificate of violation, which is simply a set of d+1 points that lies on that has an affine dimension of d-1 or lower. Here, the restriction is that these points should have d-1 or more colors, which is why we only need a weak position. With these two conditions, we can formally state the alpha version of the Ham-Sandwich theorem. Given d colors in d-dimensional space and the appropriate alpha vector, there is always a unique oriented hyperplane such that the positive half space determined by this hyperplane contains exactly alpha I points of the color pi for all I. The number of colorful sets is simply the product of the cardinalities of the colors. Each of them determines a unique colorful hyperplane. That is also the number of the choices of alpha vector. So indeed, there is a bijection between the colorful hyperplanes and the alpha vectors. However, if the two conditions, either of them, the well separation or weak general position, if they fail, then that means that for some alpha there might be no solutions, and for some alpha there might be multiple solutions. In real life, however, a ham sandwich is not well separated, so the two slices and the layer of ham between them is not well separated, even though it might follow some kind of general position. So although we can bisect it, we can never divide it into any arbitrary ratio. Let's now talk about the complexity of this problem. So Steicher and Zhao gave a prune and search algorithm to find the dividing hyperplane if the conditions of well separation and weak general position were true, and that takes this much time. This was later improved to be linear in n, but still it was exponential in d. Our aim is to understand the precise computational complexity of this search problem. So under the promise of well separation and weak general position, we know that there is always a solution for each alpha vector. However, this promise is very expensive to verify. So we would like to convert this problem into something that is a non-promise problem, something where we don't need any assumptions on the input point set. This can be done by allowing for more outputs. So if we have the input as the colors and the alpha vector, apart from having a hyperplane as a solution, we also allow certificates which witness the violations of the two conditions as solutions. Indeed, G1 is a solution that we would ideally like to have, and GV1 and GV2 tell us that either the weak general position or the well separation conditions have been violated. The theorem says that a G1 solution is guaranteed if there are no violations, otherwise there must be a violation. So this search problem is a total search problem, and this lies in the complexity class TF and P. However, we could make a more precise statement. As we saw earlier, ham sandwich lies in the complexity class TFNP. More precisely, it lies in PPA, which is related to search problems associated with Bohr-Coulomb theorem. It was recently shown that ham sandwich is complete for PPA. A subclass of PPA is PPAD, which relates to search problems associated with the fixed point theorem. Then we have PLS, which is related to local search problems. And the intersection of PPAD and PLS contains a class called CLS, Continuous Local Search. And recently, a new class was defined, which is a subclass of CLS, called UEOPL. Our main result in the paper is to show that the alpha ham sandwich search problems lies in the complexity class UEOPL. What does this stand for? That becomes more clear when we look at the problem which defines this complexity class. So let's say as input we are given a graph G which consists of a path and perhaps some isolated vertices. More precisely, each vertex has in degree and out degree 1, so it's called a line. And there is a potential associated with each vertex that increases strictly whenever we walk along the line. We are also given a source vertex for which the in degree is 0. We call this the start of a line. And then it is quite natural that there must be a sink, so a vertex where the out degree is 0, and the goal is to find this vertex. This is called the end of a line. And since there is only one path in the graph, it's a unique end of potential line. This class was introduced at ICALP last year. At the outset, this seems like a very simple problem, but the case is that the graph is not given explicitly, but rather implicitly in the form of a Boolean circuit. So a circuit that contains Boolean gates. The input to the circuit consists of n bits, and these bit strings represent the vertices of a graph. So there can be up to 2 to the n vertices. The outputs contain 2n bits representing the successor and the predecessor of the node, and some mode bits which compute the potential. So the circuit has size poly n. That means the number of gates used in the circuit is poly n. Ideally, this circuit should give us a line, but for verifying that, we need to test this circuit for all of the vertices, and that cannot be done in polynomial time. So, to handle that, as output we allow for an end of line solution, or we also allow for violations. There are 3 kinds of violations, but we need not go into the details of that. So if we don't have a violation, then we always have an end of line solution. Otherwise, there must be a violation. So this formulation gives us a total search problem. And this defines the class UEOPL. Every problem that is reducible to this unique EOPL problem lies in this complexity class. This contains problems which have unique solutions. For example, finding the fixed point of a contraction map, the p-matrix complementarity problem, or the unique sink orientation problem. Let us now try to understand the intuition behind the reduction from alpha ham sandwich to unique EOPL. Let's say we are given 2 point sets in the plane, the orange points and the green points, and we want to find a line which has an orientation such that the positive half plane contains 3 points from the orange point set and 3 points from the green point set. Let's say we are also given a tangent hyperplane, so something for which the alpha vector is 1, 1. We record this line as a vertex, and now what we want to do is we want to increase alpha for the orange point first until we reach 3, and then we will increase alpha for the green points. To do that, we fix this vertex as an anchor and we rotate the line anchored at this vertex. We get this new line for which the alpha vector for the orange points has increased by 1. Again, this line is represented as a vertex, and this edge records the rotation from this hyperplane to this hyperplane. If we continue the rotation, this time we hit a non-colorful hyperplane because it is passing through 2 green points. Now, if we continue the rotation, then the alpha vector for green would increase to 2, which we don't want yet. So we switch the anchor and we continue the rotation. This way, we reach a hyperplane for which realizes the alpha for the orange point set. So these are colorful hyperplanes, and this is a non-colorful hyperplane which was passing through the 2 green points. Now it is time to increase alpha for the green points. So we switch the anchor to an orange point and we continue the rotation. Again, we are hitting a hyperplane for which the alpha vector for the green point is 2. We continue. Now we hit a non-colorful hyperplane. If we continue, then alpha for orange would increase to 4, which we don't want. So we switch the anchor and we continue the rotation. Again, we have a non-colorful hyperplane. If we continue the rotation this time, alpha for orange would reduce. So we need to switch the anchor again and continue the rotation. And finally, we reach this line for which the alpha vector is 3, 3. So essentially, we have gone from this line to this line by a series of local changes which involves rotations, and that is equivalent to taking a path in this graph. This is a start vertex and we want to go to sink vertex by a series of local changes. More generally, the graph looks like a grid graph. So we have a vertex, which is a starting vertex, and then we can walk along one direction, increasing the alpha vector for one color until we reach the target. Then we increase the alpha vector for the second color until we reach its target, and so on until we reach the target vertex. All other vertices are self-isolated. This is the case when well separation and weak general position hold. If they do not hold, then the problem becomes more interesting. So here is a case where the orange and the green points are not well separated. If you look at H1, this contains 4 orange points and 3 green points above it. And now if we apply a rotation, then the orientation of the hyperplane flips. So H2 now has alpha vector 2, 2, which is unexpected. So this will not form an edge in the graph, although it is connected by a rotation, but the path will end unexpectedly at H1. There could be another possibility like this. Again, the point sets are not well separated, and now we have 2 hyperplanes, both with the same alpha vector, and this will represent 2 distinct lines or 2 distinct paths in the graph. Many other things can go wrong, but we can always detect them as violations. So perhaps our main contributions is trying to handle all these violations and reporting them as proper violations for the instance of alpha ham sandwich. So to summarize, we show a polynomial time reduction from an instance of alpha ham sandwich to UEOPL. This also tells us that alpha ham sandwich is supposedly weaker than ham sandwich, which was not known earlier. The next question to wonder about is that since we already know that ham sandwich is complete for PPA, is such a result also true for UEOPL and alpha ham sandwich? That is, can we show that alpha ham sandwich is hard for UEOPL? Or perhaps more optimistically, is alpha ham sandwich in P? Some related problems can also be the complexity of determining whether any given point set satisfies well separation, or to look at other ham sandwich type problems. Thank you.